on from here. I'm hoping to hit each and every indeterminate case. The most difficult ones are at the very end, from 56 to 66. Let's not choose those in the next 10 minutes. Let's practice with some other, and then we'll get to those. Those are the most difficult ones. And ready to start? Any preference? Anyone? Any preference?
Maybe 38?
We want to continue with 38. Let's do 38. And the next one I'll choose. So 38. Same page, 308. 38. 38. Limit. As x approaches 0. From e to the x minus e to negative x minus 2x divided by x minus sine x. So can anyone tell us what indeterminate case is this? And now you understand how important this is to find the indeterminate case. I want to make a correction here, sorry. This is positive and this is negative. That's the correct sequence. Sorry about that. Okay, I just look at this and I say, oh no, I think I wrote. Thank you for picking that. Okay, so when we plug in 0 here, this is 1 minus 1, which is 0, and this is 0. This is 1. This is 0, this is 0, so it is still a nice situation with 0 over 0. So this is limit as x approaches 0. I differentiate the numerator. This is nice, it's just e to the x. This is e to negative x prime, which is e to negative x, but times the inner function prime that will change this into positive. And minus 2x prime, which is negative 2. 1 and minus cosine x. I try again. This is 1 plus 1, which is 0. 2 minus 2 is 0. Cosine 0 is 1, so this is still 0. Okay, so I continue. So this is limit. So e to the x prime is e to the x. Now this is e to negative x times the inner function prime. This is 0. This is 0. Cosine prime is sine with minus in front, sine x. So the numerator is 1 minus 1, the denominator is 0, so it's still 0 over 0. And we continue. So limit as x approaches 0, the numerator, e to the x prime is e to the x. Again, now this one again changes into positive e to negative x divided by cosine x. I hope that this is it, and it is. 1 plus 1, and the denominator is 1, so the limit is 2. So in all these situations, going back, we encountered this or this, so this is the same, basically, the same treatment, gets the same treatment. So we haven't seen anything else so far. So let me choose. I would like to look at 42. At 42 I have limit as x approaches infinity from the square root of x multiplied by e to negative x over 2. Okay, so now obviously I'm expecting something else. I'm not expecting this, I'm not expecting this, I'm not expecting this. maybe this. So let's see. Where does this go when x approaches infinity? When x approaches infinity?
Towards infinity?
Yes, of course. Very good. Now, where does this go when x approaches infinity?
Infinity.
Very good. But now, where does this go when x approaches infinity? In other words, when this is negative infinity, e to negative infinity, where will that go? Where will this go? It will approach 0. So this is an indeterminate case that we may have seen before, but it's the product. 0 times infinity. So 0 times infinity cannot be treated with L'Hopital's rule. But maybe an algebraic manipulation will do the trick. I will not ever move this to the denominator, even if I could. Even if I can, I will not. Because differentiating something like this is a no-no. Differentiating this in the denominator will be tremendously difficult, and I will not get rid of it. But I see that e to negative x over 2 can comfortably go to the denominator in a simple algebraic manipulation. So I leave the square root of x alone, and this already has a negative exponent. I brought it to the denominator. And there is no change here, no difference. It's the same function. But now, I know that the numerator goes to infinity, and I also know that when this is infinity, e to infinity is infinity. And this is good, because I managed to change we're using a simple algebraic manipulation to change the product into one of these two, in this case infinity over infinity. Now I'm in business. I can apply L'Hopital's rule. So then limit as x approaches infinity. I differentiate the top, no problem. I differentiate the denominator, no problem. E to u times u prime, which is 1/2. The square root of x is prime is 1 over 2 the square root of x. And now, again, I'm trying to simplify this a little bit before I figure out how to continue. So this, I'm going to have to flip the 2, put the 2 at the top. This is in the denominator, so it comes down to the square root of x e to x over 2. And I simplify. So let's take a moment and look at this. So this is a fraction, e to x over 2 over 2. So I flip the fraction, and I get 2 over e raised to x over 2. And I put this fraction in front. And because when I divide two fractions, I put the fraction from the top in front, and I flip the denominator. So now I simplify by 2, and I get 1 and 1. But this goes to infinity, and this one goes to infinity as well, as we know. So 1 divided by infinity is 0. And I can even conclude that y equals 0 is a horizontal asymptote at infinity for this function. So what we see here is, in order to change, to try to use the L'Hopital's rule on this, 0 times infinity in this case, And you can say, but we knew that. 0 times infinity is 0. No, not necessarily. Do not conclude that's why this is called an indeterminate case. It may end up being anything. That's what's in, it's an indeterminate. In this case, it turned out to be 0, but it doesn't have to be. So, what we did, we copied the square root of x, and we changed this, brought it to the denominator because it has a negative exponent. We differentiate the top, we differentiate the denominator, and this is e to x over 2, and I flip that, and I copy the first fraction 1 over 2 the square root of x, and I flip 2 over e to raised to x over 2. We know that this approaches infinity when x approaches infinity. We know that this approaches infinity, so 1 over infinity squared is 0. Therefore, y equals 0 is the horizontal asymptote. Any questions? Any questions on this problem? Any questions? Okay, are we ready for powers? So we know these two, we had examples of that, we'll choose another, and we've seen this. So are we ready for powers? These are the most cumbersome. So indeterminate cases that are powers with L'Hopital's rule. Is that a yes, or we still want to practice with other types?
Sounds good to me.
Okay. Okay, so let's start with a an example like, let's say 57. It's in red, so let's see why it's in red. Limit as x approaches 0, they say, from, in parentheses, 1 minus 2x raised to 1 over x. Now, I'm sure that if you had any doubts why in all limits we have to plug in first, now I'm sure you have no doubts anymore. Because without knowing what type of indeterminate case, and we don't know what treatment to apply to it. Okay, so I plug it in. Where does this go?
What?
Perfect. Where does this go? Yes, you can say yes, but see, when x approaches 0 from either side, this will be infinity. And you can say no, it's going to be from the left it will be positive infinity, from the right will be positive infinity, from the left will be negative infinity. So what is it? Well, it's still 1 to infinity. So this is one of the most difficult situations. I cannot algebraically manipulate this like I did a minute ago. I was able to manipulate the product. I brought one quantity to the denominator and I changed it easily into infinity over infinity. But this one is not possible. We've had situations like these before. We looked at a function raised to another function. Do you remember what technique we applied? And you can say, well, what's this? We're not differentiating. True, I'm not. But in this situation, we applied a technique. The same technique will be applied here. What technique we... Say it again?
The chain rule?
No. So the chain rule was on this. Very good. Yes. 3f squared f prime. Yes. But on this one, we could not use the chain rule. This is a function raised to another function. What technique from chapter 2 we applied here? For a function raised to a function, and we said, oops, there is no rule for this one.
Natural law?
Excellent. So we applied log. Yes, that's the key. We do not have a rule for a function raised to a function. In this case was differentiation, but eventually that's what I'm going to do. So the first step, yes, we have to denote all this by y, which is 1 minus 2x raised to 1 over x. Then, yes, we are going to apply natural log to both sides. So natural log y is this ratio of natural log 1 minus 2x over x. So now I am going to apply the limit to both sides. And you can say no. You can't apply the limit as x approaches 0 to natural log of y. You are asked to find the limit of y. You're not asked to find the limit of natural log y. Why are you doing that? And then I'm going to say, bear with me and you'll see what happens. So I apply natural log, I apply the limit to both sides. So limit of natural log y as x approaches 0 is the same with limit as x approaches 0 from this, because natural log y and this are the same. In the next step, I'm going to ask myself, what indeterminate case is this? So, can you tell me where the numerator is going? The numerator is going to natural log 1, which is? And the denominator is going to? Yay! And you can say, well, this is good, but this is not what you are asked to find. And I will say, yes, I know. I'm not asked to find limit of natural log y. I'm asked to find limit of y. In a minute, we'll get back to that. So then I have limit as x approaches 0. The numerator prime, careful, 1 over 1 minus 2x, but multiplied by negative 2. And the denominator is 1. So now we have limit as x approaches 0 from negative 2 over 1 minus 2x. And what is the answer? The answer is? Anyone?
Negative 2.
Excellent. So now I will copy the beginning and I will copy the end. One more time. So limit of natural log y as x approaches 0 is negative 2. And now, a long time ago, in continuity, chapter 2, we had a theorem that I said is so important, but there is no need to talk about it now, although we used it in limit laws. Limit of f of g of x, we do what with the operators? And we get f of the limit of g of x. This is a theorem that allows us, under conditions of continuity, to swap the operators. Meaning, I'm swapping these two operators. So the natural log of limit as when x approaches 0 of y is what I want. So I have several ways of finishing it up. I say there is a phantom e here. E raised to negative 2 is this limit. So limit as x approaches 0, and I'm going to copy y, the original y. 1 minus 2x raised to 1 over x is e to negative 2. Or 1 over e squared. So if you tell me that you thought that 1 to infinity will end up, or you knew that we will end up with 1 over e squared, I will not believe you. So this indeterminate case for this situation turns into 1 over e squared. And that's why these are called indeterminate cases. So 1 raised to infinity is one of the powers, one of the indeterminate cases power. In this case, it was 1 over e squared. Any questions?
What's it called an indeterminate case if you determine the limit?
Because initially they are not known. Anything can happen. They're not undefined, which we know undefined is always, as a limit, is always infinity or negative infinity or d and e. But this, we have no idea. Infinity over infinity can change into 1 over 6 or 0 over 0 into 1 over 6 for one problem, into 2 for another. That's why they're called indeterminate. No idea where they lead us to. We have no clue. Indeterminate. Okay, now we are prepared to look at anything you like. So please choose anything else. We are back to page 308, and we can choose anything. So let's see, would you like to look at another power? I shut the book by mistake. Would you like to look at another power?
I think that might be helpful.
Okay. So these are the powers. If you'd like to choose anything, 59 through 66. And there are 4 more at the bottom here. We looked at 57.
Maybe something like 64?
64, very good, 64. So let's continue with 64. Which page am I on? Is it 9, the next one? Yes, I think so. Okay, so we picked 64, same page. Limit. I think it says x approaches 1 from 2 minus x and raised to power tangent pi x over 2. So let's first see what situation we are looking at. And the denominator, not the denominator, the base 2 minus 1, that approaches 1. Tangent pi over 2 is infinity. So we have the same situation, so this approaches infinity. So we have the same situation, it's a power, it's 1 raised to infinity. What will be our next step? We denote the function. And then,
Find the natural log.
yes, so we have, thank you very much, natural log y equals tangent pi x over 2 times natural log of 2 minus x. At this point, we will apply the limit to both sides and see where it takes us. limit of natural log y when x approaches 1. And we know that this is not what we are trying to do, but eventually we'll swap the operators and we'll figure out the limit. So this is limit as x approaches 1 from tangent pi x over 2 times natural log of 2 minus x. Again, I have to see what indeterminate case it turned into. I have no idea. So let's take a look. Well, 2 minus 1 is 1, and natural log, this is definitely approaching 0, because natural log 1 is 0. Okay, so now let's see this. When x approaches 1, this approaches infinity. So at this step, we managed to change the situation of 1 to infinity into a much friendlier situation, 0 times infinity, which I know that I could hopefully algebraically manipulate to change into one or the other. So this, we accomplished a big step from this to this, and I know that this should not be very, very difficult to change into one or the other. And then L'Hopital's rule. Okay, so let's see. Okay, so like with the square root, do not attempt to take natural log anywhere. Leave it alone. My chance is this. So natural log stays as is, and 1 over tangent pi x over 2, but that will be to power negative 1. Instead, I'm going to send changes into cotangent. So cotangent pi x over 2 is 1 over tangent, and tangent comes up. So I change tangent into 1 over cotangent. Maybe that's the easiest way to explain it. Now the numerator goes to 0, and I'm hoping that this goes to 0. That's my hope. Of course, it's 1 over infinity, right? So it's 1 over 0, so it has to be approaching 0. So let's see. So cotangent pi over 2, right? So if you remember the graphs, I'm going to graph both. Why not? Here's the graph of tangent. Of course, between negative pi over 2 and pi over 2. And this is the graph of cotangent. Cotangent has sine in the denominator. So this is at pi over 2. So this is the graph of cotangent. So cotangent at pi over 2 is, yay, 0. So now I continue because it's 0 over 0. So we changed again. Let me go back and summarize one more time. Where is my page? Where is my page? Okay, here. So we started with this. It changed into this after applying log. And now I changed this into this by a small or easy, I would say, algebraic manipulation. Okay then, so this is limit. As x approaches 1, the numerator prime is 1 over 2 minus x times the inner function prime. And now cotangent prime is negative cosecant squared. Okay, so now let's see what we have. The numerator, when x approaches 1, this is 2 minus 1, which is 1, but the numerator is negative 1. And now let's see the cosecant. Cosecant at pi over 2. Cosecant is 1 over sine. cosecant pi over 2 is 1 over sine pi over 2. If, because this is 1, this is 1. 1 squared is 1, with minus in front, negative 1. So finally this is 1. Don't be too happy just yet, because it's not done. I'm going to copy the beginning, and I'm going to copy the end. So limit as x approaches 1 from natural log y equals 1. I copy the beginning and the end. So now, under conditions of continuity, I will swap the operators. Natural log of limit. And now I'm going to replace the y. 2 minus x raised to tangent pi x over 2 is 1. So therefore, can anyone give us the answer for this inside? That's what we want. We want to find the limit as x approaches 1 from 2 minus x raised to tangent pi x over 2. What could this answer be? Excellent. Yes. Yes, indeed. Part 3, April 13. Okay. Very good. And again, I will not believe you. I know, I'm just kidding, you know. That 1 to infinity, you knew it was going to change into e. Because 5 minutes ago, 1 to infinity changed into 1 over e squared. So that's why it's indeterminate. 1 to infinity, and this example was 1 over e squared, and this example is e.